So I'd like to tell you today about some new directions in sort of elementary geometry that I'm pursuing with the help of my PhD students. So let's start with a brief introduction to rational trigonometry. So here are two very familiar triangles that are known to all undergraduates. So you see that they're metrically measured in unusual ways. So instead of having 1 root 2, instead of having 60 degrees or pi by 3s and such, we have these other numbers. We have a number half here, we have a number 3/4 here, we have a 2 there. These are quantities in rational trigonometry called quadrants, spread, and this A is an analog with area. So this is the starting point, and I want to tell you some consequences, how we can develop a whole new way of thinking about both affine and projective geometries in this context. A lot of different directions to go in. Okay, so there's two really basic directions from my point of view. There's affine metrical geometry and there's projective metrical geometry. And affine metrical geometry concerns a vector space, V, say, over a field F, with a symmetric bilinear form. That's the starting point. Symmetric bilinear form, like a dot product or inner product. And from that we can generate a thing called rational trigonometry, which gives simpler, more powerful, general, and accurate way of doing a lot of geometry, a lot of practical geometry. So one classical example, of course, is the familiar dot product in Euclidean space, which I call blue geometry. And then we have sort of relativistic variants where we consider sort of relativistic dot product. And these are just two different forms of relativistic dot product, which I would call red and green. So our geometries are going to work with this inner product, but also with this inner product just equally well. Another inner product that's interesting, or symmetric bilinear form, is the killing form on a semi-simple Lie algebra. We can call that killing geometry. And another very important one is what I would call operator geometry, which connects a little bit with Fedor's discussion perhaps. If you have the n by n matrices on a vector space, then that has a very important symmetric bilinear form, trace of AB. And so basically we can play the same game as we're going to do with all these other geometries. We can create an operator geometry essentially obeying the same rules. So that's all in the affine situation. There's also a projective version of all this, which is equally important, which includes hyperbolic geometry and spherical or elliptic geometries. So in the projective metrical geometry, the basic structure is a projective space, which you can think of as just the one-dimensional subspaces of a vector space. And the symmetric bilinear form on the vector space generates a metrical geometry. Okay, so let's start with the affine case. So the definition, the quadrants of a vector. So we're working in the vector space, we have a symmetric bilinear form, that's all we have. So we define the quadrants of a vector, V, to be V dot V. We make sure not to take the square root. We are not interested in taking the square root because that takes us outside of pure mathematics as far as I'm concerned. It's an applied mathematics concept because it requires an infinite amount of operations. We don't do that, we stick with the quadrants, and here's our notation for quadrants, and here are the two most important theorems concerning quadrants, and perhaps the two most important theorems in geometry. The Pythagoras' theorem is that these two sides are perpendicular, and perpendicularity in this general context simply means that the dot products are 0. Precisely when Q1 plus Q2 equals Q3. And the second most important theorem in geometry, as far as I'm concerned, is this one here, which perhaps you don't know, but you should. It concerns three collinear points, and three quadrants is formed by three collinear points. Q1, Q2, and Q3, and the collinearity is reflected in this somewhat more complicated relation. Q1 plus Q2 plus Q3 squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared. Okay, to replace the notion of an angle, we introduce the idea of a spread. So the spread formed by two vectors, V and W, is, here's the crucial definition, 1 minus V dot W squared over Q of V, Q of W. And Q of V is V dot V, W dot W. So we're not taking any square roots and we're not taking any cos-inverse functions. We're sticking with the algebraic concept, the pure algebraic concept. Very important. Okay, that's called the spread. It has an interpretation as a renormalized determinant. Another way of thinking about it is you just take the determinant of the quadrilateral form and renormalizing it by the quadrances of the side so that it's independent of scaling. Of course, in the Euclidean case, it's also the sine squared of an angle, but we don't need to transcendental notions to work with this concept, which works much more general. Okay, I make lots of YouTube videos and I have lots of correspondence with people all over the world over these things. And the fellow from the Isle of Wight, Paul Miller, came up with this dramatically simple physical explanation of what a spread is. Okay, so here's just an ordinary semicircle, linear scale 0 to 1. Here we have one line and another line making a spread S. What is the meaning of the spread S? You go up to the circle and you drop down and you read off that linear variable. Very beautiful. It's another way of thinking about what the spread is. It's actually much simpler to make such a protractor because you don't actually have to separate the circle. You're just dropping down from the circle. Okay, the main laws of trigonometry, besides the two that I've told you, if you have a triangle with three spreads, S1, S2, S3, and three quadrances, Q1, Q2, Q3, then here are the main laws of trigonometry. This is the algebraic replacement of the cosine law, this is the algebraic replacement of the sine law, and this is the algebraic replacement of the fact that the three angles sum up to 3.1415926, blah, 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 blah. These laws work in all of those geometries, all the affine geometries that I mentioned. They're completely general laws. And they work over a general field. Okay, now let's talk a little bit about the projective version, where I'm interested in one-dimensional subspaces of the say, a vector space. So I have lines through the origin coming out, and we can visualize it on the surface of a sphere if we like. We have a spherical triangle formed by these 3 points. We're going to make corresponding definitions. So a projective point is a line which is homogeneous coordinates x, y, z. A projective line in this context is a plane through the origin, which has, again, the plane can be represented by Lx plus My plus Nz, so the normal vector gives us coordinates for the plane. So these are lines and these are planes, or just projective points and projective lines. And then the projective versions of the affine concepts I told you about are these ones here. The quadrants, projective quadrants, and projective spreads are just defined by exactly the same rule as we use to define the spread. 1 minus dot product squared over dot product dot product. But now there's a symmetry in the situation, which means that the whole thing is symmetrical between the points and lines as we're used to in projective geometry. Okay, so if we have 3 such points, we have a projective triangle. We can talk about its 3 quadrances and its 3 spreads. And then here are the main laws for projective geometry in the setting, metrical projective geometry. We still have a projective spread law, which looks exactly the same as before. But now the cosine law, the cross law is jacked up, something a little more complicated. Very beautiful formulas, lots of things one can say about them. Anyway, so those are the projective analogs of the cosine law. Okay, so now we're in a position to study 3-dimensional geometry. It's a highly neglected subject. It's really remarkable that in modern mathematics, the geometry of the world in which we live in is so neglected. Even if you take a icosahedron, which is, or dodecahedron even better, which is studied from the ancient Greeks, and you ask some elementary questions about what's the angle from this point to this point to this point, you don't have proper answers to that because the notion of angles is not the right way of thinking about things. With rational trigonometry, you can study all these things and you get true answers and they fit together all beautifully. So here's just a very simple example of a regular tetrahedron. Connected a little bit with Nikolai's talk, well, this is just the Euclidean setting. So it turns out that the numbers that you get are like this. The quadrum, which is essentially the volume, is 2. The face quadrias, essentially area squared. 3/4 represents the 60 degrees on the angles. The dihedral angles are replaced by dihedral spreads, which are all 8/9. It's a very important number for a chemist. Well, the angle is very important. Someday the spreads will be more. And the solid spreads, we can define solid spreads in this context by essentially going to the projective setting that I talked about, and they turn out to be a half. And one can do this, one can study a lot of situations very concretely. Okay, I want to talk a little bit about relativistic geometries. And so going back to the planar situation, here's the red in the product, the relativistic in the product. I'm just illustrating Pythagoras' theorem here. That's a right triangle. In this context, these two lines are perpendicular in the red setting. And there's the corresponding green version of Pythagoras. And now here is a very interesting thing that happens, which I call chromogeometry, which is that if you combine the blue and the red and the green geometry, then you get a remarkable threefold symmetry in planar geometry, which seems to have been completely mysteriously unobserved until now. There's a remarkable threefold symmetry that makes us want to go past the Erlangen program. So no longer is geometry the study of the group acting on space, because there's more than one group acting here. You cannot escape it. So notice these are the altitudes. So if you have a point and a line, these are the 3 altitudes of the different colors to the line. And we notice some pleasant conditions that the red altitude and the blue altitude are green perpendicular and cyclical. Okay, so here's chromogeometry manifesting itself. I could talk a lot about this diagram, but let me just show it to you. So here's the triangle A1, A2, A3, and here are the 3 orthocenters. Okay, there's the familiar blue orthocenter, which is just the Euclidean one. It turns out that the other geometries, the triangle, the altitudes of the triangle intersect, and you get orthocenters. And they form what I call the orthic triangle of the triangle. And that orthic triangle is quite interesting because the midpoints of its sides are the circumcenters. So the midpoint between the red and the green orthocenter is the blue circumcenter, which is the center of the blue circle that passes through the 3 points. But similarly, the center of the green circle, which in this case is a hyperbola, is between the red and blue. Then you see various pleasant things that the red and the green orthocenter, for example, lie on the blue circumcenter and other pleasant things. This is chromogeometry. The idea that these 3 geometries interact in an intimate way. Okay? And if you want to discover new facts about geometry, here's a recipe. You take your favorite Euclidean result, you study the relativistic versions, the red and the green ones, and then you put all 3 together and see what happens. 50% chance you're going to get a new theorem. Okay, here's a result of Nguyen Lei and myself, my student who's doing a filming here. So this is concerning, it's also a chromogeometry result. Here's a triangle, it's a rather small triangle. Okay? And we see its 4 incenters. Okay, the 4 incenters are in blue. There's one there, there. And this triangle is chosen so that it also has 4 red incenters and 4 green incenters. So with the appropriate notions of what an incenter is in the relativistic geometry, there's 4 red ones and there's 4 green ones. And it turns out that the blue and the red incenters lie on a single green circle. So the 4 blue incenters are actually cyclic with respect to the blue geometry, and they're cyclic with respect to the red geometry. But moreover, the blue and the red incenters lie on the same green circle. And you can see that. So here's the green circle, for example. That's a green circle. And it turns out that that circle has centered the green orthocenter. There's the orthic triangle I showed you previously. Here's another example of chromogeometry. Here's a parabola with a familiar Euclidean focus and Euclidean directrix. It turns out that you can define and study parabolas in the relativistic context as well. Same definitions. So you could take a red focus and a red directrix and ask for all the points which are equi-quadrants from the point and the line. And that's the same parabola. And we see, rather surprisingly, that the red and the green foci determine the blue directrix, while the green and the blue foci determine the red directrix, and so on. Okay, finally I want to just briefly dip our toes into the hyperbolic geometry. Okay, so this is the big story. So my student Ali Al-Talmi is just finishing his PhD, and it's all on hyperbolic geometry and study of parabola in particular mostly, and related things. And so here's a particular result from that. It's all done in this framework of rational geometry, because there's no transcendental quantities at all. So where is hyperbolic geometry here? Well, so for those of you who know some hyperbolic geometry, sort of following Nikolai's thing, we're looking at the Klein model here. So this is the unit circle in the complex plane. This is the Klein model where the lines are straight. Okay. This is a parabola, and it has foci and a directrix, and another foci and another directrix. And there's many beautiful things, but this is just one of many theorems illustrating how we can actually construct the evolute of this parabola using ruler and compass, well, not just ruler constructions. So the center of the place where adjacent normals to that point meet is this point here in this construction. So much more to be said, but I think this general orientation opens up a lot of new areas for the investigation. Okay.
So, are there any questions, please?
No, do you have a nice interpretation of the theoretic principle in projective geometry?
Oh, which one?
The theoretic principle.
Duality
Yeah,
between...
theoretic principle. Like three projective line concurrent, right? The dual is...
Yeah, so in the projective geometry, the duality is built into the metrical structure by the symmetry between the projective quadrants and the projective spread. So the duality is a thorough duality. If you replace points and lines, the whole thing is symmetric. Yeah.
As far as I understand, is using spreads and is a new convenient just language of speaking of classical fields.
It's much more than that, though, because it extends the geometry to situations that are unfamiliar. In particular, we can do geometry over finite fields, and we can do geometry with not necessarily positive definite quadratic forms. For example, the operator geometry, the trace forms are not necessarily positive definite. But the formulas still work, we can still do geometry in that context.
And the results that you get using these new language can be reformulated in the standard language of angles and...
They can be, yes, because you can replace, you can restrict yourself, say, to the interior of this disk, for example. That's classical hyperbolic geometry. Then you can interpret the spread and the quadrants in terms of the classical ones, and you can convert all the theorems into classical ones. But their domain of validity will only be inside here, while we see that they're actually valid everywhere. Thank you.
Are there any other